Hey folks, a lot of people are worried about the quiz and the test. Someone asked for some review prompts, so I did make a sheet of them. It's on the canvas, you've probably already seen it. And what I'm going to do here is I'm going to record videos of me doing at least some of them, so that way you all can see how I work through them, and hopefully that'll help out a little bit. So first, 4.1. This is a problem someone asked me about something similar to in class. Problem 1 is sketch a continuous graph, f, a function f that's continuous, that is continuous from 1 to 5 inclusive, so that's hard brackets, including 1 and 5, and has the following properties. We need an absolute maximum at 5, an absolute minimum at 2, a local maximum at 3, and a local minima at 2 and 4. Okay, how might we do this? Me personally, I think about it in steps. So first we know an absolute maximum has to occur at 5, right? So we go to 5, and I'm just going to make a dot here, just a point that's as high as possible. I know however I draw the curve, I'm never going to get higher than that. Similarly, for an absolute minimum at 2, we're going to have, let me put a little mark here, I'm going to have a slow point at 2, posed a little awkwardly, the apartment's a little not conducive to this sort of thing. And we're not going to go below that. And then finally, we have a local maximum at 3 and local minima at 2 and 4. What's that mean? Well, if we have a local maximum at 3, that means we have a point that's not as high as 5, but is higher than the points around it. What does that look like to us? Well, we're going to go to 3. We're going to just pick a y value. We're going to have one that's bigger than our absolute minimum, lower than our absolute maximum, and I'm going to draw basically a little hill like that. This is an absolute not an absolute maximum. This is a local maximum. It's not the highest point ever, but if we come up to 3, we can see it is higher than the other points around it, the other areas of the function near it. Similarly, at 2 and 4, we're going to have local minima. They're going to be lower than the points around them. So we have 2, which is obviously going to be lower than the points around it. And then for the point at 4, we're going to have something that's not as low as 2, but is still lower than the other points around it. It's kind of like at the bottom of these valleys. And then finally, what we're going to do is we're going to just pick some, since 1 isn't anything, we're just going to just give it a y value. It's not going to be like a local max or min. It's just going to be there. It's just an endpoint. And we want to graph a continuous function with all of these properties, right? So what we're going to do, what we can do, is we can just carefully connect all of these with a single line. Note that we didn't introduce any other hills or anything like that, no additional hills or valleys. We just have absolute minimum at 2, absolute maximum at 5, local maximum at 3, and local minimums at 2 and 4. So that's what the first one looks like, right? All right, had to pause and come back. This is problem 2. We want to find the critical points. Of this function here, t to the 5th plus 5t to the 3rd plus 50t. Okay? So, what are critical points? We talked about proofs and theorems in class, but the important thing is this. Critical points of a function, like the critical points of g of t, are just the places where the derivative of this function, so that's going to be g prime, are 0 or non-existent. So first let's take this derivative. 5t to the 4th plus 15t squared plus 50. Right? Cool. Now, again, we want to find the critical points of this function right here. And critical points are places where the derivative of this function, so that's this one right here, equals 0 or the function does not exist. Okay. And we'll talk about why those matter for a later problem. But for right here, we just need to find it. Now, this is a polynomial, and this is a polynomial. Polynomials are those smooth, continuous curves we think of when we think about functions. And, oops, gotta be careful I don't tilt this in the future. All we're going to do to find critical points here is we're going to set this equal to 0, and we're going to solve for t. We're not going to worry about where this is defined because polynomials are defined for all real values. So let's start. We're going to take this derivative, 5t to the 4th plus, I suppose that does show up, plus 30t squared plus 50. Noops. Apologies. We're going to set the thing equal to 0. 15t squared plus 50. Something we're going to want to do, we're going to divide by 5 on both sides. So we get t to the 4th plus 3t squared plus 10. Did I put this in right? I suppose I must have. Alright, I did not put it in the practice problems right. It should be t to the 5th plus 5t to the 3rd minus 50t, and then this is the derivative, and we're setting it equal to 0. Normally, I would edit this video to just so you don't have to worry about that, or edit the practice problems, but the test is in a couple of days. I gotta make a lot of these. We're all in a bit of a time crunch here, so just bear with me. We're going to set the derivative equal to 0, and we're going to solve for t. We're dividing by 5, and that gives us this. And this t to the 4th, t squared, nothing at all. That's basically a binomial, not a binomial, it's basically a quadratic form. Let me show you what I mean by that. If we can factor this, so it's t squared times, we're going to have t squared plus 5, times t squared minus 2. Okay. So, this is our derivative. We've divided by 5, and we factored it, and we can use this to find places, values of t, where this derivative equals 0. So we have two possible solutions. We have t squared plus 5 equals 0, and t squared minus 2 equals 0. Now solving this is pretty easy. We're just going to bring the constants over. T squared equals negative 5. T squared equals 2. And we're going to solve for t by taking the square root of both sides. Can't take the square root of this one because we can't take the square roots of negatives. T squared equals 2. Let me just draw an arrow. That is going to mean t can be plus or minus the square root of 2. So, this here is our critical points. Because we took this function, we found its derivative, and the only t values where this function equals 0 are t equals plus or minus the square root of 2. If you don't believe me, I recommend you plug this into Desmos and you can graph it. And that's going to show you just there's exactly 2 roots, plus and minus square root of 2. So that's pretty cool. Let's do another one. Alright, here's the third problem. We're still finding critical points, except this time the function is p minus 1 divided by p squared plus 4. Now to find the critical points, it's the same thing. We're looking for places where the derivative equals 0 or doesn't exist. So to start, we're going to find the derivative. We're going to have h prime of p, and we have a fraction, so we're going to apply the quotient rule. Let's see. Low d high minus high d low over low squared. And we're going to simplify this a little bit. P squared plus 4 minus 2p squared plus 2p. Because we're multiplying this negative 1 times 2p, and we're subtracting it. And this is all divided by p squared plus 4 squared. And let me just minus p squared plus 2p plus 4, all divided by p squared plus 4 squared. And again, we're looking for places where this derivative equals 0 or does not exist. Let's start with doesn't exist. In Calc 1, we're mainly concerned with 2 ways that a function can exist, sometimes 3. First, you cannot have a 0 in a denominator. You can't divide by 0. You cannot have a negative in a square root, or really an even root, but principally we're dealing with square roots. And then finally, you can't have a 0 or a negative and a natural log. Those are basically the 3. Now, we don't have a square root, and we don't have a natural log, so we don't have to worry about those. We do have a denominator, so we have to think about that one. But p squared plus 4. P squared is always positive, so p squared plus 4 is always also going to be positive. We can plug any value of p we want in here, and the denominator is going to be non-zero. So we don't have to worry about the derivative not existing. Sometimes we do, but not here. Now we just have to worry about the fraction equaling 0. When does that happen? When the numerator equals 0. So we're going to set the numerator equal to 0. P squared, I'm just going to multiply this through by a negative. It'll be the same results. P squared minus 2p minus 4 equals 0. We're going to factor. So we have okay, so we're going to have p. Does this factor? Minus 2, that's 4 minus 1. It doesn't, I don't think. So we're going to have to apply the quadratic formula. Minus b plus or minus b squared minus 4ac divided by 2 times a. I'm going to take a minute to resolve this on my own. Okay, I applied the quadratic formula, and you can see that the values of p that solve this, that make our numerator equal to 0, that make our derivative equal to 0, are 2 plus the square root of 20 divided by 2, or 1 plus or minus the square root of 20 divided by 2, or if we simplified it even further, 1 plus or minus the square root of 5. So that'd be about 3.236, and negative 1.236. That's not important. You could leave it in this form, or this form, or in this form on a quiz or in a test, and that would be perfectly acceptable to me. The important thing is that all of these quantities represent the same thing. The two numbers that make our derivative equal to 0. These two numbers, 1 plus the square root of 5 and 1 minus the square root of 5, are the critical points for this function because they make our derivative equal to 0. Let's figure out why the critical points are important. I lied. We're going to find the critical points one more time for this function, just to show you what it looks like for trig. Now, again, critical points, looking for places where the derivative equals 0 or does not exist. Okay, so we're going to start by finding a derivative. Using what we know about trig, this is going to be negative 2 sine of theta plus, this is a chain rule, so we're going to have 2, because the exterior function is x squared, we're going to take the derivative of the outside function. X squared becomes 2x. We're going to plug in the inside function where that x would be, so it's not 2x, it's 2 sine of theta. And then we're going to multiply by the derivative of that inside function. Derivative of sine is cosine. Okay. Now again, looking for places where this equals 0 or doesn't exist. We're not seeing any denominators. We're not seeing any square roots. We're not seeing any logarithms. Tangent, you can't plug pi over 2 into a tangent. That's another place where things don't exist. But you can think of that as a quotient, because tangent is sine divided by cosine. Point is, for this problem, we are only concerned with where our derivative equals 0. So we're going to set this equal to 0. Negative 2 sine of theta plus 2 sine theta cosine theta. And then, there's a couple different ways you could deal with this. Me personally, I am going to factor 2 sine out of both of these terms. So we end up with negative 1 plus the cosine theta. Okay, so we have two possibilities. Sine of theta, if sine of theta equals 0, this whole thing equals 0. And similarly, if cosine of theta minus 1 equals 0, then this whole thing equals 0. Right? So, where does sine of theta equal 0? Well, we know that by the unit circle. It equals 0 where the y value of the unit circle is 0. So that's going to be 0, pi, 2 pi, 3 pi, 4 pi, whatever. Theta equals n pi, where n is just some integer. It's just some number we can name. It could be 5, a million, negative 3, whatever. Okay. Now, for this one, we're going to solve cosine theta equals 1, and what theta values give us a cosine of 1? Well, we know that from the unit circle too. 0, 2 pi, 4 pi, 6 pi. Theta equals n times 2 pi. Just multiples of 2 pi, right? Okay. So these values create for us, they give us a derivative that equals 0. Now, multiples of 2 pi are also multiples of pi. So for the critical numbers here, we would just say it's n pi. For any multiple of pi, we have a critical number. Why are critical numbers important? Okay, so just before we get into any of the problems, I'm going to talk about this. Critical numbers, we're interested in critical numbers because they tell us where maxes and mins can be. And we talked about theorems in class, but I'm just going to speed run it. Look at this curve. Pretty normal, right? Now, where are the local minimums? Well, that's obvious. They're here and they're here. These are the places where the function cannot get any lower. Well, it's not like it can't get any lower, but we have a point that's lower than any of the other points around it. You can think of it as the bottom of a valley. Okay, that's reasonable enough. Now, what is special about these? Well, if they're going down and then they don't go any lower, the tangents for this are flat. The tangent lines have a slope of 0. Now, what tells us the slope of tangent lines to our curve? The derivative. Every time the derivative equals 0, we have a place that can be a maximum or minimum. It's like up here. This tangent line's horizontal. That's a local maximum. Up here, this tangent line is horizontal. This is a local maximum. This is why we look for places where the derivative equals 0, because every time we have a local min or a local max, then, like these, one of these where it's like smooth and continuous, the derivative equals 0. Now, not every critical point is a maximum or minimum. Consider the graph like x cubed, right? There's a point right here where our tangent line is flat, where it is horizontal, where our slope is 0 and our derivative is 0. But obviously this is not a local min or a local max. There's places around it that are lower, there's places around it that are higher. So not every critical point, even the ones where the derivative equals 0, are local mins or maxes, but every max and min that's continuous like this is going to be a place that's a critical point. Now, we also, when we think critical points, we also think places where the derivative doesn't exist. Why is that? Well, there's some maxes and mins that occur where derivatives equal, well, where derivatives don't equal, where derivatives do not exist. Think about, if you will, the absolute value function. This is something we talked about earlier in class. The absolute value function does not have a derivative at this point, at this x equals 0 point. But it's definitely a local minimum. It's lower than all the points over here. It's lower than all the points over here. So this is a local minimum, but the derivative doesn't exist. And that's basically why when we say critical points, we mean everywhere where the derivative equals 0, where the tangent lines are horizontal, flat, or places where the derivative doesn't exist. Because for a local min or max to exist, it has to be at one of those two places. Not every critical point is a minimum or a maximum, but every maximum or minimum is at a critical point. Okay. Now, I'm going to show you how we find these maximums and minimums. Okay. So this is a problem where we're going to find absolute minimums and absolute maximums using what we know about critical points. We're going to find the absolute max and min of this function. F of x equals x plus 1 over x on this interval. 0.2, that's 1/5, to 4. How do we do that? First thing we always want to do is just take our derivative. This one's not going to be too bad. Derivative of x is 1. Derivative of 1 over x, or we can also think of it as x to the negative 1 power, derivative of that is negative x to the negative second, or alternatively, we can write this as 1 minus 1 over x squared. Okay, so this is our derivative. It tells us the slope at any point for this function. And we want to know where the slope is 0, or when we have a corner or a cusp where the derivative doesn't exist, that can be a local min or maximum. Okay? So, first let's think about where does this derivative equal 0? If we have 1 minus 1 over x squared, we're just going to set that equal to 0. We can start solving this by addition. We're going to add 1 over x squared over, and we're just going to solve for x. X squared equals 1. Solutions, x equals plus or minus 1. Okay, so this derivative equals 0 wherever x equals positive 1 or negative 1. But We're only concerned with points between 0.2 and 4. 1 is between 0.2 and 4, but -1 isn't. I know it's kind of a duh, but I'll bring it up anyways. So we're only concerned with x equals 1. Let me put this in a box. Critical points. X equals 1 is a critical point for us in this interval. It's something we need to look at. X equals 1, -1 is not. We're also going to look for places where the derivative doesn't exist. Well, there's no natural logs. There's no square roots. There is a denominator, but this function does not exist when x equals 0, because we have a 0 in the denominator, right? But 0 is not in our interval. So we don't need to worry about x equals 0. The only point we're concerned with, it seems, is x equals 1. That's it. Okay, so we have our critical points in the interval. What do we do with them? Here's what we do. I'm going to box this off. We're trying to find the absolute maximums and minimums. We know that any sort of like local max or min has to occur at a critical point, but absolute maxes and mins can also occur at the endpoints of intervals. So like here's an example. I'm just going to draw this real quick. Okay. So let's say this is the start point and this is the end point. Well, we have local mins and a local max, but the absolute maximums occur at the endpoints, even though they're not critical points. They might still be continuing upwards. So when we're finding absolute maximums and minimums of a function like this, we check the critical points and we also check the endpoints of the interval, even if they do not make our derivative 0, if our derivative does not exist. So the points we're investigating are 0.2, 1, and 4. What do I mean by investigate? Well, we're looking for the absolute maximum and minimum, the absolute highest point and the absolute lowest point, right? So what we're going to do is we're going to take this and this and this, we're going to take our three values, and we're just going to plug them back into this original equation. And the reason we do that is because this tells us the height associated with each of these 3 points. And once we have those 3 heights, we can compare them against each other, see which one's the highest and which one's the lowest. Let's start with an easy one. We're going to go with f of 1. We're plugging 1 into our original function. That's 1 plus 1 divided by 1. F of 1 equals 2. Let's do f of 4. Now, f of 4 is going to be 4 plus 1 over 4. 4 plus 1/4, 4 and 1/4. Or 4 and 2, 5, 17/4, whatever works for you. I'm not picky. Last but not least, we're going to do f of 0.2. And that's going to be 0.2 plus 1 divided by 0.2. And this is going to be easier if we think of 0.2 as 1/5. Because then we have 1/5 plus 1 divided by 1/5 is 5. 5 and 1/5. Okay? Well, we've investigated our critical points and our endpoints. We have heights. Which one is the biggest? 5 and 1/5, right? So the absolute maximum value of x plus 1 over x on 0.2 to 4 is 5 and 1/5. Cool. And the absolute minimum value, the lowest of these 3, is 2. If you have a TI-84, like a graphing calculator, or you go on Desmos, you can check this yourself. Graph x plus 1 over x, change the axes to be from 0.2 to 4, and you'll see that this is the lowest point, and this is the highest point. That's basically the process for any time we find absolute minimums and maximums. We're going to be given a function and an interval. We're going to take the derivative. We're going to find all the critical points, all the places where it equals 0 or doesn't exist. And we're going to take all those critical points. We're going to take all those endpoints of the intervals. We're going to plug all of them, one at a time, back into the original function. The absolute lowest value is our minimum, and our highest value is our maximum. And all the other points might be like local mins or maxes. They're not the absolute highest or lowest, but they're the highest or lowest compared to points around them. And we'll talk about how we find that out. Okay, I just realized to skip one of the problems. We'll leave it be. That's a good one to try on your own. You can graph it, you can see, you can compare its results to your own. I want to show you one with trig. Also, I'm getting hungry and I want to get to dinner sooner rather than later. I'll admit that. We want to find the absolute maximum and minimum of f of x equals 1 plus cosine squared of x on the interval from pi over 4 to pi. What do? We always start, when we're trying to find the absolute maximums and minimums, we always start with the derivative. Okay, so derivative of 1, 0. Cosine squared, that's a chain rule, just like the one we did earlier with sine squared. This time it's going to be 2 times cosine of x times negative sine of x. So our derivative equals negative 2 cosine of x sine of x. Okay. Well, let's think about it. No square roots, no logarithms, no denominators. We don't need to worry about this derivative not existing. Let me turn this so it's a little more visible. We are only concerned with where this derivative equals 0. Now, we can break this up into two parts. This equals 0 if the cosine or the sine equals 0. So let's break that up. Cosine of x equals 0. What x values have a cosine of 0? If we think back to our unit circle, we know that x is going to be pi over 2 plus multiples of pi. So that's going to be pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, you get the picture, right? And sine of x, if we set that equal to 0, then that gives us x values of, that are just multiples of pi. So that's 0, pi, 2 pi, 3 pi. Okay. Now here's the question. These are all the places where the derivative equals 0, right? But we're only concerned with points within this interval. So, pi over 2 is in this interval. Are any of the other critical points in this interval? No, because if we add pi or subtract pi, we move outside of the range from pi over 4 to pi. Similarly, if x equals n pi, then all the multiples of 0 or 2 pi, those are outside the range. The only critical point that's in the range is pi, so we're going to write that down. Let me write that up here, actually. Critical points. We're going to have x equals pi over 2 and x equals pi. Okay. Now, we have 4 points to check. We're going to plug in pi over 2. We're going to plug in pi, because that's where our derivative equals 0. Those are possible local mins or maxes. And we're going to plug in the endpoints of our interval. So let's get to work. F of pi over 4 equals 1 plus cosine squared pi over 4. Well, cosine of pi over 4 by the unit circle is the square root of 2 over 2. So we're going to have 1 plus the square root of 2 over 2 squared. So we have 1 plus 2 fourths, or 1/2. And you can write this as 1 1/2 or 3 halves. Whatever's fine. We're going to plug in pi, that's the other endpoint. 1 plus cosine squared of pi. Cosine of pi is -1. So we're going to have 1 plus -1 squared. 1 plus 1, 2. F of pi over 2, we're checking our critical points now. Pi over 2, we have 1 plus cosine squared, pi over 2. Cosine of pi over 2 is 0. So we have 1 plus 0 squared, which is 1. And then last but not least, we're going to check pi. Oh, well, we already checked it, didn't we? All right, so which one's our absolute maximum? Which one's our absolute minimum? Max, min. And you could just say like, oh, like f of, like, not f of. You could say 2 is our absolute maximum value and 1 is our minimum value. You could say like, oh, we have a maximum at pi 2 and we have a minimum at the point pi over 2, 1, and that would also be fine. I'm not massively picky with how you write your answers, as long as I know that you mean the y value of 2 is as high as we get, and the y value of 1 is as low as we get. That's all I really care about. That kind of concludes the practice problems for section 4.1. I'll post this on Panopto or YouTube if that doesn't work, because I have never used Panopto once and said, oh boy, I sure am glad Panopto exists, right after I used it. So we'll see. Also, YouTube would let me divide this into chapters. I don't know if Panopto does that. That might be a handy feature. I'll get back to you. Alright. I'm going to take a break for dinner, because I think it's 6 or 7. I don't have any clocks. I'm going to take a break for dinner, and I'm going to get to work on 4.2. That's going to be Rolle's theorem, mean value theorem. And then later, after that, we're going to do 4.3, which is kind of like introducing things we can learn from derivatives, first derivative, second derivative. That seems to be a place where lots of people are struggling. And then 4.4, L'Hopital's rule. 4.5, we're going to practice some graphing. And then 4.7, which is applied stuff. So keep an eye out for that.